Hey everyone, myself Bhavya Goyal, a student at IIT Gandhinagar. I welcome you at CodeChef and let's have a look at this question. So yeah, today we'll be discussing this question set to median. In this question, we're given an integer array A of length n and we can do the following operation at most once on an array. That is, we choose a subsequence x1, x2, dot, 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 xk such that 1 is less than equal to x1 less than x2 less than xk dot, dot is less than equal to n and get the median of the chosen indices inside our array A, and we set all the elements in our subsequence to V. So less formally, what we are doing is pick a subsequence of elements of A and then replace all of those elements inside a subsequence with the median of the subsequence. So let's say we had an array like 1, 3, 5, 2, 8, 7, and we chose the elements 1, 2, and 7, then what we can do is we'll get the median of this subarray, which is 2 in our case, and replace all of these elements by the median. And our goal is to maximize the sum of the elements once we have done the operation at most one time. And we need to print the maximum of whatever it is. In the constants, we're given that the test cases will lie in between 1 and 10 raised to the power 4, and will be in between 2 and 2 into 10 raised to the power 5 and a of I will be in between 1 and 10 raised to the power 9. And we are also given that the sum of n over all the test cases will not exceed 2 into 10 raised to the power 5. So seeing the constraints, what can you think about the time complexity, the expected time complexity? We can't have a we can't have a of n square complexity, right? So it has to be of something of the order either n or maybe something like n log n, right? Now let's look at the sample input ones. In the first input, we are given 3 and 4, which is our two size input array. Now, if we do the operation on just this element, then the median will be changed to 3 only. If we do the operation on this element, then the subsequence will change to 4 only. And if we choose both the elements as a subsequence, then we'll have 3 and 4. The median is 3. So we'll replace both of them by 3 and the answer would be 6, which is not better, right? So the maximum sum which we can get is 7 only. That is by either doing operation on just this element or just this element or not doing the operation at all, right? In the second input, we are given 3, 4, 3, and 1 as an input array. Now, the maximum what we could do is choose all the three elements, and the median of all the three elements would be 3. So we'll replace all of these elements by 3, and the maximum sum which we can get would be equal to 9. You can try out the rest of the cases by yourself, and I'll discuss the solution now. So, okay, step 1. Now, the very first thought, will sorting the array change anything? No, right? Because we just need to choose some subsequences, and out of the subsequence, we are replacing them with a mean, right? So it does not have anything to do with the order of the elements of the array which we have, right? So what we'll do is we'll sort the array A, which is our very, very first step. Now let's say that we have some elements like this. We have, let's say, 8 elements like this. And inside a subarray or subsequence, we choose these four elements, A3, A4, A6, and A7. And what would be the median of these four elements, A3, A4, A6, and A7? That would be A of 4, right? Now, what we'll do is we'll replace all the elements by A of 4, right? So this would be A4, this would be A4, this would be A4, and this will also become A of 4, right? Now, notice here that because our array is sorted, right? Because our array is sorted, we know that this will give us a positive sum, right? This will give us a positive gain because A of 3 was less than or equal to A of 4, but now it is equal to A of 4. So the overall sum has increased. But these two elements are going to give us some negative gain, right? Because earlier they were bigger elements, but now they are smaller elements. So it is better to remove this element from a subsequence, right? So if we do not consider this, we'll be having just these three elements, right? And it is better to not consider this A of 7 and the median is still the same A of 4, right? So by doing all of this, all I want to show is that the subsequences we are choosing must be of odd length. Choosing a subsequence of even length would never give us a better answer than choosing one of an odd length. It may give equal answers, but choosing an odd length will always be better. Right. Now let's discuss the solution once. So for now, let us say that we fix A of 5 as a median. It could be an element, it could have been some other A of I as well. But for now, let us say that A of 5 is our median element, right? Now, what options do we have? We just keep A of 5 only and take the sum, right? Or we add one element to both the sides of A of 5, right? Because we want A of 5 as the median. So what we do is we take one element from here and one element from here, and A of 5 will still remain a median, right? So what is the best element that I should be choosing? It should be A of 1, right? Why? Because I want to maximize our sum. And to maximize, this A of 1 will get converted into this A of 5. So this A of 1 is the smallest element. And if I make it A of 5, then I'll be having the largest gain possible, right? And these elements are going to reduce in the magnitude. So it's better to choose the smallest element to reduce in magnitude, right? So if I want to choose one element on both the sides, let's call the number of elements we are choosing as k. So if I want to choose one element on both the sides, they would be these two elements, right? Now, what if I want to choose two elements? They would be these two elements, right? If we want to calculate three elements, it would be these three elements, right? And so on. Because, and what would we be adding? The what we are adding is going to be equal to like the new sum minus the old sum. So what would be our new sum? It would be 2 times k times a of 5. So here our k is 3. That is, we're choosing three elements on both the sides. On each side, my each element value is going to be equal to a of 5. And in total, I'm changing this for 2k elements. So 2k into 5 would be my new sum for these 5 elements. And what was our old sum? It was this sum a1 minus a2 minus a3 minus a6 minus a7 minus a8, right? And we just need to maximize this for all the possible values of k for this particular a of 5, right? Now, how do we know that how many elements should we choose? What should be the optimal value? And before that, I hope everyone knows prefix sums already. So before that, we can easily calculate these sums effectively using prefix sums, right? We can first calculate the prefix sum. Let's call P as our prefix sum array. So it would be nothing but P of K plus P of this I. If this is I, then I plus K minus P of I. I plus K minus P of I. This would be our sum of these two arrays, right? And our new sum would be nothing but 2 times k times a of 5 minus this thing, right? Now we need to figure out that how we can choose some optimal value of k to calculate that if I keep a of 5 as a median, then what is the most optimal value of the number of elements I should be choosing each side? And if I can calculate that optimally in, let's say, something like constant or log and time, then I can easily brute forces for all of my indices and calculate the answer, right? So for that, notice here that we'll be first of all adding A1 and A6. And these are the first elements we'll be considering. So what we're adding is A5 minus A1 plus A5 minus A of 6, right? So it is equivalent to 2 times A of 5 minus A1 minus A6, right? Now what if this is when my K was equal to 1? Now what if my K is equal to 2? It would be A5 minus A2. So what I would be adding is 2 times A of 5 minus A2 minus A6. If I choose K equal to 2, then I'll be adding both of them, right? If my K is equal to 3, then I'll be adding 2 times A of 5 minus A of 3 minus, sorry, this would be A of 7 here, and this would be A of 8 here, right? So I'll be adding all of these things, right? This would be my new contribution, right? So this is what I'll be adding for if I keep on changing K, right? Now notice that this thing is decreasing in order, right? Why? Because here A of 5 is constant. This A of 1 is increasing as we go down, right? A of 1 was smaller, then A of 2 is bigger. So I'm subtracting a bigger value, right? This A of 7 is also bigger, right? So as I'm going down, these values, all of these values, they're decreasing in order, right? So for k equal to 1, it was the biggest. Then k equal to 2, it gets smaller. Then and then it keeps on getting smaller, right? And I'll be adding the prefix of these values as my answer, right? So can I binary search on it now? So up till some k, these values are going to be positive, and I would be taking the prefix sum of all of them. And after a point, they'll start getting negatives, right? At some key. So if at any point this thing gets less than zero, I'll stop. So I need to get the largest index such that this value is positive, right? And if I can get that largest index, and I can easily get that largest index using binary search, right? And using in like log and time, using prefix sum and binary search, we can calculate for some idx or for some I, what is the best possible answer I can get by keeping that element as the median of the whole array or the whole subsequence that we are choosing, right? And this is pretty much the whole solution. So just to summarize it, so what we are doing in a final algorithm is we're trying all the possible values of I as our possible median. So we're checking that what would be my maximum possible answer if my IDX or if my current I is the median. And then we are using the binary search to find the optimal size of the subsequence, right? So if my this is the IDX I'm choosing, what is the most optimal number of elements I'll be choosing to the left and to the right using binary search? And then we're taking the maximum possible gain we can get for all the possible values of x. And the time complexity for this is n log n. So yeah, this is pretty much the whole solution. I don't think so. Yeah, I hope it is clear. Now let us see the solution, the code. So this is the solution in C++. So we begin by taking an input of each test case and calling this solve function. Inside a solve function, we'll take in the input of all the elements. We'll take in the input of array and the total sum. We also calculate the prefix array on the sorted array. We initialize our final answer, which is the maximum gain we can get as 0. And in the end, we'll print the maximum gain plus the total sum we already had. We are running a loop from 2 to n minus 1. Why? Because the minimum I have to select one element, right? Selecting a single element won't be beneficial, so it won't really matter. We're defining a lower limit as 1 and the upper limit is the min of number of elements in to the left of IDX and the right of IDX. While L is less than or equal to R, we're calculating the mid. We're calculating 2 times A of IDX minus A of mid minus A of IDX plus mid is greater than or equal to 0 or not. If this is true, we are increasing our search space. So earlier we had a big search space. We checked for the mid and we saw that, okay, up till here, all the elements, all the gain I'm getting is positive. So increase the subspace to this much part. Otherwise, we're decreasing our subspace and we're just calculating our answer for the best possible value of k we got. And we're taking the max of it over current answer and the max we can get using this idea. And in the end, we're just simply printing the answer. Now let's see the solution in Python. So we'll begin by running a loop for each test case. We'll take in the input of n. We'll take in the input of the array A and sort the array. We'll define the prefix array and take the prefix and define the total sum as this total sum. We'll define an answer which will store the maximum gain that you can get as 0. We'll run for each IDX. We'll put the lower limit of our binary search as 1 and the upper limit as the min of IDX minus 1 and n minus IDX, which is min of the number of elements to the left of IDX and to the right of IDX. We initialize the best possible k we can get for this IDX as 0. We run our binary search and define our mid to be L plus R by 2. Now, if at any point this condition is true, that means we can go further in a subspace. That is, if this was my total search range, this is my mid element, and up till mid also my gain is positive. That means I can change my search space from here to this much part. So I'll increase the L2 at mid plus 1. We have got the most optimal case so far, that is mid. Otherwise, just reduce our search space from L comma R to L comma mid minus 1. If our k is greater than 0, this does not really matter that much. But anyways, if our k is greater than 0, we'll calculate this well, which is the current gain that we can get, which would be 2 times A of IDX into k minus the old sum. So this is the new sum we'll be getting. And this is the old sum, which is prefix up till k, which is like the first k elements. And these are the k elements right after the IDX. And if this well is greater than our answer, we set this answer as well. And this pretty much solves the question. The time complexity again is n log n because we're running a loop. And then for each element, we are doing this binary search. So yeah, this is pretty much the whole solution. I really liked it. Thanks.